Hello, everyone. Good afternoon. My name is Ana Carvalho, and as usual, I'm here today with my colleague Inês Almeida to present you with the R&D sessions by EDP New. We are really happy to have you here today for our 27th edition. For those who don't know, EDP New is the R&D center for EDP, and we work on research and development projects on the energy sector. We work on European projects looking at innovative solutions for the decarbonization, the smartification, and the flexibility of this sector. Since 2020, we've been organizing these R&D sessions in a monthly basis, and this is where we get together experts to discuss several topics regarding the future of energy, the challenges that we're facing, and also the solutions that we are already putting into practice to revolutionize the sector.
For today's sessions, we are going to dive into the topic of vehicle-to-grid technologies. And in this regard, we will introduce you some of the R&D solutions that are being deployed in this area and how the adoption of electric vehicles can contribute to protecting our grids. Let us remind you that the recording of each webinar is available on our website. You just need to read the QR code in the slides and you will be able to watch them offline. For today's webinar, we want to encourage you to use our Q&A chat to ask your questions to the speakers. And at the end of the presentations, there will be the opportunity for them to answer. With no further delays, we welcome you to this event and wish you all a great session, but not without first introducing you our moderator, João Mateus. João is graduated in electrical and computer engineering by Instituto Superior Técnico and postgraduated in project management by Lisbon School of Economics and Management. He has more than 15 years of experience in the energy sector and worked in areas such as network protection and automation, software development in power systems simulation area, power systems consulting, and technical sales for grid simulation. In the past years, he has worked in several projects related with grid flexibility and battery energy storage systems. And nowadays, João is a senior R&D project manager in European funded projects in the electromobility and grid resiliency areas. Now, João, the floor is yours, and thank you all.
Sorry. Thank you, Inês. I'm just with my microphone. Good afternoon to everyone, or good morning, conforming place you are assisting this webinar. It's a pleasure to be the moderator of this session. Before move forward with our topics, I would like to thank you, our speakers that join us today and participate in this R&D session. Okay, the agenda for today. First, I will give a quick introduction about the context of electromobility and the importance of it in our future. Next, Samuel Matias from EDP will talk about the evolution scenarios of electric vehicles in Portugal. The third point will touch the vehicle to everything strategies and will be conducted by Professor Hugo Moraes from INESC-ID. And final but not least, Fernando Henriques from Eletricidade dos Açores will present the grid operator point of view about the demanding caused by the vehicle electrification. And we will finish our session with a Q&A slot. Please don't be shy. Write your comments and questions on the chat, and we'll be glad to answer you. So, in first place, I think it's important to present some facts and figures and keep this in mind when we are talking about electromobility these days. For example, in the first place, the transport emissions represent around 25% of the EU's greenhouse gas emissions. But for example, the transport sector is also an important one in the European economy because it contributes with the 5% of the European GDP and around 10 million people are working in this in the transport sector. On the other hand, we have that the transport sector is one of the sectors with the lowest use of renewables energy sources, and it's very dependent from fossil fuels. But on the opposite side, we have the power sector that is one of the sectors that with more renewable penetration and with a growing tendency. And for example, the share of renewables in electricity generation should increase from 26% numbers from 2020 to 90% in 2050. And if we funnel our vision to cars, we find that almost 243 million cars circulate nowadays in EU roads. Also, we have today, and this is numbers from 2021, we have an important market sales offer in terms of models that using electric engines, around 450 models. And this number is expecting that will grow in the coming years. And why it will increase? Because the car manufacturers are no longer pursuing the internal combustion engine as the main avenue of their research and product development. And the proof of that is the car manufacturers' investment estimated for the next 5 to 10 years is around 515 billion euros. And of course, for the same period of time, we are expecting more products on the market. Now, if we change a little bit to a perspective of the timeline, we should put some events on this timeline. And for example, these days, COP27 is happening in Egypt, and probably more outcomes should be expected. But let's look a bit to the past. For example, to COP21, where the Paris Agreement took place. We were in 2015, and it was agreed to limit the global average temperature grow in 2 Celsius degrees, comparing with the pre-industrial value. So it was pointed a horizon of 35 years to do everything that we can to achieve this target. If we move to last year in Glasgow, also during the conference COP26, we had governments, car manufacturers, and investors that issued a joint declaration proposing 100% of zero-emission vehicles, at least the new vehicles that will be on sale by 2040. This is a global target. For lead markets, should happen 5 years earlier. And in this case, Europe is one of these lead markets. And because of this, our European Parliament approved this year the end of sales for internal combustion engine vehicles by 2035. But this is what we know. Let's look to the future and what we have in front of us. And we have also some important milestones in the horizon. The first one is in 2030, and where European Union pointed to have at least 30 million zero-emission cars on the European roads. To compare, today we have around 5.5 million electric vehicles circulating in our roads. So we are talking about multiplying by more than 5 times this number in around 8 years. Also, it's expected that 100 European cities will be climate neutral. In terms of mobility, this means that the vehicles that will circulate inside the cities must be zero emissions. For example, full electric cars and plug-in hybrid cars that have a certain range of pure electric mode. On the other hand, it's expected that the cars moved by internal combustion engines should be forbidden to circulate in these 100 European cities. After that, if we look to 2035, and I already pointed it, we had no more new cars with internal combustion engine. And finally, the most ambitious target for 2050, where we would like to have almost 100% of cars, vans, buses, heavy-duty vehicles with zero emission. So with all of this in mind, we comprehend that we have a lots of challenge in front of us, and challenge in different ways. We can start by talking about the acquisition costs. Nowadays, we have higher prices for electric vehicles. We can talk about confidence of people in this new technology. We can have also some reluctance to change because, for example, of the range anxiety connected with electric vehicles. Our cities needs to adapt, and we are starting this process, but many work needs to be done to consider this mass deployment. Also, the infrastructure for related with the charging points for the electric vehicles needs to have many more points of charging, public and private. We also talk about challenges related with the interoperability between the different players, car manufacturers, resellers, energy providers, system operators, etc. But the most important is the impact in the electrical network. If we have more electric vehicles, this for sure will mean a peak demand and a change in the way the network is being explored. The point is, the electric vehicles are not a common load. EVs, the electric vehicles should be seen as a tool capable to create a kind of win-win situation for the electrical grid, for the renewable generation, and also for the user. Let's point some examples. For example, smart charging. Smart charging enables the possibility of peak shaving and load shifting. For the grid, this means reduce the congestion, but for the user, can mean a lower price because the vehicle will be charged using electricity generated by renewables. If we look to the vehicle to everything, by definition, we are talking about putting the vehicle communicating with grid, with buildings, with parking lots, with houses, basically with everything around the vehicle. And this leads to different advantage. Not only, for example, in the situation of the vehicle to grid that can contribute to stabilize the network, but also in terms of energy efficiency, in terms of the buildings, and so on. Finally, and to give the floor, to give the stage to our speakers, let me just present two projects that EDP New is participating. Is two projects funded by Horizon Europe. We explore precisely the vehicle to everything concept in terms of technology, use cases, business models, and strategies. And both projects pointing to a scenario where we have mass electric vehicles deployment. The first one is EV4EU that started on June 2022, so started this year, with a duration of 3.5 years and the overall budget of 9 million euros. 16 partners from 4 countries plus 6 associated partners. The Inesc ID is responsible to the coordination of the entire project. The purpose of EV4EU project is propose and implement bottom-up and user-centric vehicle-to-everything management strategies, creating the conditions for the mass deployment of electric vehicles. The strategies will consider and is considering the impact on batteries, in user needs, on power systems, energy markets integration, and the city's transformation. And all the proposed solutions during the project will be tested in 4 demonstration sites: Portugal, Denmark, Slovenia, and Greece, covering a total of 12 use cases. 5 of them will be tested in the Portuguese demonstrator, located in São Miguel Island, in Azores. One of these use cases will be related with grid services, where the electric vehicle can provide some power to the network to contribute to the grid stability, but also helping in the integration of the renewables energy. EDP New is coordinating the Portuguese demonstrator with the support of Eletricidade dos Açores. The second project is Drive2X that will start in the next January 2023, with a 4 years duration. The overall budget is 10.5 million euros, 18 partners from 8 countries. LUT University in Finland is in charge of this project coordination. It will consider 5 demonstrator sites in United Kingdom, Portugal, Hungary, Netherlands, and Italy. The Portuguese demonstrator will be in the north of Portugal, in Francisco Sá Carneiro Airport near Porto in Maia, where vehicle-to-X solutions will be tested and taking the advantage of the available flexibility brought by the batteries of the electric vehicles parked at the airport for long periods of time. Also, EDP New is coordinating the Portuguese demonstrator with the support of airports. And now it's time to move forward in our agenda and give the floor to Samuel Matias to talk a little bit about electric mobility evolution in Portugal. Samuel Matias is an R&D project manager in EDP New and serves on electric mobility projects. Prior to joining EDP New, Samuel was working in the transportation sector and was responsible for infrastructure monitoring and design. Previous to his work in the transportation industry, Samuel was a fellow researcher at Instituto Superior Técnico on R&D projects in the domain of innovative solutions for railway engineering. Samuel earned his PhD in transportation systems from the MIT Portugal program and a master's degree in civil engineering, both from Instituto Superior Técnico in Lisbon. His main drive is the development of innovative mobility systems to enhance the decarbonization transition. Samuel, please, the floor is yours.
Hi, João. Thank you. I'm going to share my screen. I think everyone can see my screen now. So thanks, João, and thanks everyone that is participating in this session. Today, I'm going to present the electric mobility evolution in different scenarios for Portugal in the upcoming future, and why that's important. So see, so a small introduction on the V2 concept that already João presented, introduced the topic. So the V2X concept is mainly is the possibility of a set of a vehicle or a set of vehicles can communicate with an external entity like a ISO, and this entity can request a signal from these vehicles to, for instance, supply power where consumption is. It can be like self-consumption in the case of a home, or in the case of a district or a block, and you can provide it, or even the entire grid to provide energy upon demand of this entity, external entity. So this concept is gaining some traction all over the world. Currently, there are more than 70 projects in Europe, with 3 projects in Portugal. Some examples of the ones that João talked previously. And before we start, I would like to ask the audience on the idea of how Portugal ranks on the electrical mobility market share in the worldwide. Do you think it's like top 50, top 20? You guys can answer, drop the answer on the chat, and I will give you some time to think on that. Currently, Portugal has around 90,000 electric vehicles, with a 50-50 share between full electrical vehicles and plug-in hybrid vehicles. And that corresponds to around 2.5 gigawatt hours of stored potential energy, which is around 2% of the total daily energy consumption of the country. So let's back to the question that I did previously on how Portugal ranks worldwide on this electrical mobility scheme. So Portugal is currently top 9 on the world regarding the electrical sales of electrical vehicle sales in the country. As you can see, most of the countries that have better performance than Portugal have way higher GDP. So if you consider that the GDP and the fleet renewal of Portugal, it is actually top 3 in the entire world. So Portugal is a good nest to test this V2X technology. So this drives us to 3 scenarios in which we have a conservative scenario that is an off-track course of action. So the targets that we defined for the Paris Agreement will not be met. There will be some resistance of adopting EVs. Then we have the progressive scenario in which we keep the current trend that we've been working on, and the introduction of new mobility solutions like shared mobility. And finally, we have the disruptive scenario, where there are very favorable conditions to adopt EVs as a mobility solution, and that will cause a dramatic rise in mobility needs. So moving to the conservative scenario, this one, as I said, the carbon reduction targets will not be met until 2035, and after 2035, some internal combustion engine vehicles will keep being sold, and that means to a total fleet by 2040 of around 1.7 million cars, with 1 out of every 4 electric vehicles being a plug-in hybrid. And that translates to around 78 gigawatt hours of stored energy, which is around 60% of what we consume on a daily basis today. So even so, it's a conservative scenario. It's not that negligible to account for. Next, the progressive scenario. In this scenario, it's the most likely in which we keep our current trend of the electrification of our fleet. In this scenario, the plug-in hybrid solution will play a major role on the transition phase that will slowly fade away after 2035. And then a steady pace of a growing number of fully electric vehicles. And by 2040, we'll have around 3.2 million vehicles, which would be reflected in around of more than 150 gigawatt hour of potential energy stored. That is over 100% of what we consume in the country on a daily basis today. And with this scenario, we will meet also the 10 EVs per charger metric. That is a metric the European Union defines as a goal for the number of chargers in the network. Finally, the disruptive scenario. This is by far the most demanding scenario from electric supply, energy supply point of view. In this scenario, there is an aggressive adoption of EVs that only starts to fade at around 2035 to 2040. In this scenario, there is a high usage of individual cars, so a real great number of EVs. So with this scenario, we have around 6 million cars by 2040, which is around 85% of the entire fleet. And it will be translated in more than 300 gigawatt hours of energy that is potentially can be stored in the vehicles, and that is over 200% of what we consume on a daily basis. So it's a really big storage capacity that we can have to use to supply for the grid. This last scenario, and in the sense to validate this modeling, we can compare to a real example, a real world example, like what's happening in Norway. If we take the evolution of the EV market share, the full electric vehicle market share in Norway, and shift for around 6 years, we can see that it meets our modeling of disruptive scenario. So we can sense that there is some coherency on the data that we did. And with that, we don't know what the future holds, but we know that the reality for Portugal will be a combination of these three scenarios for the different parts of the region. Probably a more urban part could translate in a more disruptive scenario, and a more suburban could be like a conservative or progressive scenario. So it would be a combination of those different scenarios. And with that, I've reached the end of the presentation. So feel free to drop some questions in the chat, and I'll be happy to answer at the end of this session. Thank you, and back to you, João.
Thank you, Samuel. And now it's time to move forward for our next topic about vehicle-to-X management strategies. Our speaker is Professor Hugo Moraes, that received a master's degree from the Polytechnic of Porto in 2010. and a PhD degree in 2012 from the University of Trás-os-Montes e Alto Douro, all in the field of the electric power system. He is a senior researcher at Inesquide and an assistant professor at University of Lisbon. His research interests are in the development and deployment of smart grid methods and tools. He participates in the definition of operational planning tools used by the French DSO, the development of hardware agnostic solutions based on IEC standards to be used in power substations and to control distributed energy resources, and in the test and validation of tools to be used by an aggregator providing multiple services at the same time. Hugo, the stage is yours. Thank you.
No, can you hear me?
Yes.
Yes, I think so. Okay, thank you very much for this introduction, and thank you also for this invitation and for the organization of these events. Today I will talk a little bit about the management strategies that we can use in V2X, because we are considering that vehicles can be charged, but can also be discharge some energy, and this energy can serve for buildings, energy communities, grids, and whatever. I will start with with a short introduction of control technologies that we can use for electrical vehicles. And as you can see, we have different mechanisms, and we can do a direct control of these vehicles using contracts or not, or consider different type of contracts. We can use mechanisms based in price, based in markets. We can have some autonomous control where we have intelligence in the devices, in local devices that control the EVs, or we can have some specific contracts where we have variable capacity. This means that, for example, in some hours we have one capacity to be used for the vehicles, and in other hours we can increase this capacity because we know that the network is not in peak hours. We don't have any other consumption. This is possible exactly because, as mentioned by João, the electrical vehicles is a special load where we have a lot of different solutions that normally are not proposed for the normal loads. If we go a little deeper in this analysis, what is the best methods for control? In fact, is not best methods. The methods have advantage and inconvenience, and we should look in different perspectives. For example, if we compare direct control with dynamic tariffs, in the direct control we have a more effectiveness in the solution, but we also have more investment and more computational effort. When we use dynamic tariffs, the investment is much lower, and if we have a large dissemination of these tariffs, probably we will obtain a similar result. By the way, we also have some regulatory constraints here, if we can apply or not. We have data constraints regarding the GDPR, but in fact we have different options that we should think what are the best ones. I will talk in different in these slides in different types of management in the houses, in parking lots, a little bit in the by virtual power plants. I will start from houses, and I will talk not only in the management of vehicles, but also in management houses in general in that case. Here is one example.
It seems that we have some problems. Maybe we lost. Hugo, are you there?
of one application that
Hugo, are you hearing me?
yes, yes.
Because we lost you for maybe 5 to 10 seconds.
Okay, I will continue. I think I'm sharing my screen.
Yes,
right?
yes, you are.
Okay, sorry. I'm explaining that the goal of this project was to develop the management of one house where we have some appliances, we have electrical vehicles, we have some generation. Here is a schematic. This is the real implementation of this house, and here I will only talk in some problems that we have. Here we have the management structure that we implemented, where we have, as usual, this data acquisition, we have the actuators, and here we have some intelligence that we implemented for controlled loads, but also to identify some use profiles of the user, some context regarding if we have persons in house, if we are in summer, if it's raining, and so on, because the profiles of the persons or the behavior of the persons can change. And here I'm talking more about the implementation. And here, for example, we are talking about the fridge model, where we have here a very interesting equation. In fact, we changed a little bit the mode of operation of this fridge, because this is a normal operation, and we allow simulations in temperature inside the fridge. But the main problem is when we compare this interesting model with reality, we have something like this, that this is real measurements, and this is what we expect with our model. And this is only to say that sometimes when you use this in our simulations, it's very interesting, but in real life, sometimes we have this kind of problems. Of course, this is not very complicated to solve. We can easily only have a multiplication factor, and we can more or less have the same behavior in theoric and the application, and this is fine. If we look, for example, in one room, and we want to control the heating in one room, it is more complicated because we have much more parameters and that we should consider. And in that case, the equation is a little bit more complicated. But when we look in the real behavior and in the theoretical one, we can see that here in this phase during the night, we have one kind of deviation. Here is completely different, the behavior between the theory and practice. In that case, we changed this initial model, introducing these new two parameters, and we try to optimize these two parameters to minimize the errors, and we obtain the curves like we have here in the right side. This is the result. In that case, we are using this time of use prices or real-time pricing. Of course, we have these curves where we have different behaviors for the vehicles, for the heating systems, and so on. And in fact, here is obtained based in real measurements. Moving for parking lots. If you want afterwards, I can give you more details about this, but we don't have a lot of time. Here in parking lots, I will present two examples. One example is typically when we have a house or a building, when we have apartments, and the people want to install more charging stations. But in fact, the problem is we don't have enough power in the parking lot. We don't know exactly what is the state of charge of the batteries because they don't have communications in most of the charging stations. And in fact, we should have some solutions to manage the charging in these parking lots. What we did is try to develop some rules based in fairness, and we test this. We have here two scenarios. The first one is considering that the first car that arrives to the park is the first that should be charged. And here we use these fairness rules, where we will split the charging between the cars and giving opportunities for all the cars to be charged. Here we consider charging stations with different capacities. In fact, here when we use these 120 kilowatts and 250 kilowatts, we are assuming that we have for more than one place. And here we can have this conclusion. And if you look for these two first assumptions, or for these two first charging powers that are more usual, that we have 7.2 or 22 kilowatts, we can see if we don't have any strategy, we will have some cars that will need to depart from the parking lot, but the charging station is still at 10%, 20%, 30%. And if we use this strategy, that in that case, we are assuming that we don't know the state of charge, we don't have any communication with car, we are only controlling the charge. And we can arrive much more interesting solutions where the minimum state of charge is 70% for this car. We can also imagine that we have different type of contracts, saying that we have, I put here BIP, VIP, that is very important persons that are the ones that really want to charge the cars in front of the others, and because of this pay more for this kind of services. And we can also compare what happens if we don't have this type of contracts and when we have this type of contracts. In the second example is a completely different example. It's also in a parking lot, but we are talking in the parking lot with a public parking lot where we can schedule, we can book the parking. And here the perspective is the management of charging will be integrated with management of the park. This means when we arrive to the park, we will click in one button and we will say, I need to enter in the park, and the park, the management will say, okay, we should park in this place. And we will park in this place because we know that we have availability in terms of charging stations, in terms of electrical circuits and whatever. We have a lot of constraints in this case. Here, we did in fact, hierarchy level, because we have different levels of control, and we also have a dynamic in the time of the optimization. In fact, when first car arrive, we will place one place. So we'll demand to park in one place, and we will see with the optimization what happens in these 5 hours ahead, because it's the period where the car will be parked. But when the second car arrives, we will extend the period of optimization and so on.
Hugo,
afterwards, yes, almost.
Just try to keep.
Yes. Okay. Here I have one example of virtual power plants. What is interesting here is that we have the network inside, and we can optimize the cars with the different assets, including the networking, and we model this using one AC power flow, what is a little bit complicated. We have here some results, and here we have one example where we are managing the cars, not based in the direct control, but based in the prices. And here we have some relations between the market prices and the wind factor. And we will propose tariffs, different assumptions of tariffs, and we will see what happens in terms of charge. Only to finish, I will only introduce the EV4U project that João already introduced. Here I have a little bit more details, but only to say that we will is a very ambitious project where we will see the integration of vehicles in different kinds of assets, or in houses, buildings, parking lots, and companies, for example. But we'll also see what happens in the integration of power systems in the electricity markets and in cities. That is something very important. We have here some use cases that João already talked of use cases from Portugal. We have the other countries. And only to conclude, we have here the social networks. If you want to see some information and see what happened, what is going on in the project, please feel free to go and to this social media.
Thank you.
Okay. Thank you, João, and thank you for the alert.
No, just to keep the session in time.
Yes, of course. Okay.
Okay. Moving to our last topic about the e-mobility from the DSO point of view. Our speaker is Fernando Henriques. He's an electrical engineer who has been making his career mainly in Eletricidade dos Açores, in the planning department for generation, transmission, and distribution systems. And he is currently responsible for the innovation and technical planning department at Eletricidade dos Açores. Fernando, the stage is yours. You can share your screen and proceed. You are muted.
Okay, thank you for the introduction. I would like to thank EDPNU for the invitation to talk in this session about the electric mobility from system operator perspective. The Azores Islands are a group of 9 volcanic islands located in the middle of the Atlantic Ocean between Portugal and the US. Each of the 9 islands has its own electric system and is responsible for its electric generation. They operate independently from each other since there is no connection between them, and there is no possibility of exporting or importing renewable energy between the islands. The annual electrical energy production in Azores is around 800 gigawatt hours. Eletricidade dos Açores is the system operator of all islands. It develops its activities on generation, transmission, distribution, and commercialization of the energy. It's responsible for the modulation of peak energy production by installations connected to the public networks, and is responsible for all the ancillary services required to maintain the electric system reliable, stable, and secure. To this end, EDA still needs to operate some diesel power plants that continue to be a vital asset for the island microgrids. About electric road mobility in the Azores, there are about 236,000 inhabitants, around 164,000 vehicles. That's more than 1 vehicle for every 2 inhabitants. But the number of electric vehicles still represents about 0.5% of the global number, even though sales of these vehicles are growing year on year. Since 2019, the installation of public charging points has been promoted. Today we have about 29 normal charging point stations and 18 fast charger stations that are in all islands. For the electrical system, it is important to have flexible and smart charging. So these are not the ones that we would like to be more used. About the benefits of the electrical vehicles, there are, as you know, there are many advantages from the electric vehicles over the traditional vehicles with internal combustion engines, which helps their rapid acceleration in EV uptake and may exceed even the best forecasts. But what drives the end user to buy one electric vehicle? There is the environmental. It is friendly. It is less green gas emissions, less noise. It is better performance, superior energy efficiency, lower maintenance required, simpler in terms of mechanical complexity, with fewer moving parts, more reliable. Okay, I will not talk about this, but less noise for the peoples, easy home charging, lower cost per mile, and less stress from stop-start driving for the people. Okay, these will be the user benefits. More important is the global benefits for the region, for the country, for the Europe, for the world. It's the decarbonization of the economy, reduction of energy dependence, reduction of environment footprint, and increase of transport energy efficiency. Okay, then we have the system operator. For the system operator, there are not only benefits, but also challenges and opportunities. You could say that the load increase would be a benefit, but that's not it as it seems, because that means an increase in power production and in energy transmission, which leads to more investments and more operational costs. And the load increase introduces even a greater difficulty in reaching the target of 100% renewables. So there will be challenges, such as the need to support the load growth. We need to increase renewable production. We need to upgrade distribution grids. And there is the need also to do real-time management of electricity flow. We have to improve the monitoring and control systems, and we also have to promote demand-side management. And there are also opportunities such as to have more resources to increase renewable integration in the island's load diagram, promote, encourage ancillary service, and optimize grid utilization. But for that, the technology must provide smart and flexible charging, which ensures a daily optimized charging schedule for EVs to prevent potential congestion and to flatten peaks, and will be especially helpful to allowing EVs to draw on renewable energy. So the electrification of transport is of main importance for the decarbonization of the economy, and will bring the main benefit, but to bring the main benefits wanted for individual users and for the entire community, it is needed a shift in electric generation to more renewable production. This is the big challenge, a big challenge here for us. So now we have about 35% of in renewable share. In last year we had 38. We had a problem with geothermal here plants in São Miguel Island. You can see here the generation in each island. You can see that the biggest represents about 50% of total generation. The second one, terceira, about 25, and the others, the rest, the remaining 20%. So we want to increase the renewable production. For that, we have to build, and we are building new facilities. We have the expansion of geothermal power plants, as you can see here. We have the renovation and expansion of wind farms, the construction and expansion of PV power plants, the construction of hydropower plants, and also we need some systems to help to introduce this energy to the grid. We have here energy storage systems, and with them, and to control this, all this, we need also energy management system. So what we pretend is to achieve about 56% in the next 5 years. So also there is a trend in the grid transformation called decentralization, where the customers are becoming active elements of the system. Various technologies are evolving with different implications for the grid. We have distributed generation from renewable sources, primarily PV, which helps to reduce demand during sunny hours. We have distributed storage that helps to flatten the demand peaks and valleys. We have energy efficiency, which reduces overall demand, and demand response, which reduces peak demand. And additional, in the electrification process, we have the electric vehicle that's associated with technology that provides smart and flexible charging. That it's important. They may bring benefits to the electric system from its storage and demand response capabilities. Daily optimized charging schedule for EV may prevent potential congestions and flatten peaks and help harness renewable energy. So we have here an example of what can be done with storage. We have here the frequency control, the regulation done by diesel power plant. We have the change of the loads, consumption. You can see when we increase renewable energy sources, intermittent renewable energy sources, there is a change in the frequency. It's harder to control. And then when we put a big energy storage system, it can help in this, not only frequency, also voltage, but I didn't brought here. This is real data. This is from Graciosa Islands with a big BESS system. So this is what we want from the batteries from electric vehicles, not at this scale, but they can help. And here you can see the daily load curves in each island. You can see that they vary. It depends on the season. The maximum load usually is at night during the autumn and the winter, and during the midday during spring and summer. Okay, this load. The best, what we would like would be to flatten these diagrams so that we could use the installed power capacity of the wind farms and even from geothermal plants. So what we want to do is some load shifting from the peak hours to the valley hours. And this with the help of the vehicle, the electric vehicles. So what we have here is a project vehicle to grid in Asia that was developed here in São Miguel Islands. And it was promoted by Galp. And the main goal of this project was to test the vehicle to grid technology, analyze and quantify the benefits for both the client user and also the grid operator. This project had these partners, Nissan as Automobile Technology, that provide the vehicles and the knowledge in vehicle to grid technology, the Magnum Cap, the charging technology provider, Nuve as the responsible for the management and aggregation platform and for the setting of desired vehicle to grid functionalities, and then ourselves, the grid operator, as and the owner of the electric fleet. Then we had also Ines Tech, who made both the technical and economic evaluation of the project results to see the benefits from the vehicle to grid. We had also ERS and the Portuguese energy regulator and national and regional government bodies followed this project to consider its results in the development of future legislation and regulation. So the project goals will be to use the time of use tariffs, to do the peak shaving, to give services to the grid, peak reduction, frequency regulation, voltage control, and to compensate the renewable frequencies, the renewable energies intermittence in the frequency. So we have acquired 10 Nissan vehicles with technology vehicle to grid capability. They were used during the day and plugged over the night. So we had about 15 hours a day of vehicle to grid operation per electric vehicle. The car had to be connected to the chargers. And here you can see a live dashboard showing the active power flows, connection status and state of charge. Here the 10 vehicles and here the power flows. This is from Nuve.
Fernando, can you try to conclude, please?
I'm just finishing. Yeah. So with this project, We had one use case, a case scenario, the load shifting scenario. And with this, you can see that in time of use profile, the time periods when the vehicles here are being charged or being discharged, or if they are in power safe mode or in trip mode. You can see here that during the peak hours, they would discharge. During the valley, they will charge, and during the day, they will be used by the users here in the company. This functionality fulfilled the intended objective in terms of services provided to the electrical system. However, the values estimated as benefits for consumers were not what was expected. Then we have here another use case scenario with frequency regulation. You can see here in the red periods, the frequency regulation, and this is the charging here during the valley hours. So to do this, the vehicles needed to be plugged to the charger devices. So this scenario is not intended for company vehicles, which are used during our working hours, but to the vehicles from people, mainly to get and to go back from work. From this study, we could see from this use scenario that the EV chargers respond correctly to the frequency variation. You can see here the frequency variation and their response. They will charge energy in the vehicle batteries when the frequency was higher, and will discharge when the frequency was lower. Although to have a positive impact for the electric system, the frequency sampling and power set point should be lower. So the frequency sampling and power set point delays should be lower, and in most cases, because taking that time, they could impact the EV participation in frequency regulation. With the substation EV fleet above 3.6 megawatts performing frequency regulation, these delays that we had here in this user case, it could jeopardize frequency behavior, leading to severe oscillations. So this is possible, but there has to be some improvement in the frequency sampling and power set points. Time delay. So these are the big numbers. We also have monitored the state of health, and it was similar to the normal vehicles that we use here. We have about 20 vehicles, electric vehicles, not with this technology vehicle to grid, but the state of health was, the health depreciation was similar. And during these 582 days, we had 109 megawatt hours energy discharged to the grid during the peak hours. It was enough to power 32 homes and to avoid emission of 15.2 tons of CO2. Now we have another project that I'm not going to talk about because it was already told to you from Hugo Moraes. But we have also here a pilot, here also in São Miguel Island. We have the ASER's user case, one vehicle to grid station, and some vehicle to X to houses, to buildings, and to companies. So this is our experience with vehicle technology, electric vehicle technology.
Thank you, Fernando. It was a great presentation, and thank you to our all speakers. And now it's time. We are in fact a little over time, but I believe we have some space to put some questions on the table because we have many participants, and thank you to the audience to put your questions. Okay, let me try to check the list. Maybe the first one will be to Samuel from Gonçalo Pinto Mendes. Isn't a disruptive adoption scenario more in line with the very aggressive car manufacturer investment trends that we are already seeing, and thus more probable? can you comment on the role of standardization as determinant factor of either adoption scenario?
Well, thanks for the question. It's a very interesting question with a not so simple answer, but the answer is yes. The car manufacturer has the power to induce demand on the car sales. However, it's not the only player, and not the only stakeholder involved. Other stakeholders, city planners, can also have a big impact on the number of EVs on how the mobility scenarios can develop. So, for instance, there are some car manufacturers that are thinking on business models that will stop selling cars and instead they just sell a subscription to a car. And that has a great impact on a number of vehicles. And of course, answering on about the standardization. Of course, the standardization and the trying to lower the costs of EV, like EV mobility, has a great impact on the number of sales. So, if the car is cheap and there are conditions to use the car, people will use the car. So this modeling has that into account. And I saw another question about the number of electric vehicles and and should be a more usage of public transport instead of EVs, and that goes again to the stakeholders involved, namely city planners. And trying to summarize, the city planners, they have the power to strangle the use of the car. So because being electric is not the solution for the future of mobility. Public transport and shared mobility is, but cars will be around a little longer because people are still buying them. And in every scenario, the car ownership actually it decreases. Even in the disruptive scenario, there are fewer cars than there are today. So, for instance, the progress scenario, today there are about 7 million cars, and by 2015 there will be 5 million. So, in the modeling, they're accounting for a reduction on the number of cars, but there are a lot of stakeholders involved, like the car manufacturers, city planners, even the users can have an impact on that. And well, it wasn't a simple answer, but I hope I answered the question that you did.
Thank you, Samuel. Moving to the next question from Giannina Cardenas. I don't know who wants to answer. Maybe you, Hugo. But let me point the question. At the moment, we have different renewable technologies that are being applied to supply energy. How far are the application of these technologies in vehicles in massive production and more affordable for the final consumers?
I don't know if I completely understood the question. If it is to apply the renewables in the vehicles or is to coordinate the production of renewables with vehicles, because they are two completely different things. I think that for the coordination between vehicles and the production of renewables, it is not so far because we can do this in houses, for example, or in buildings. Is something that we show that we can do. For example, I show in my presentation the coordination in one house between the production, between some storage and the electrical vehicles. If we talk, for example, in coordination between wind farms and PVs, is a little bit more complicated because we need to understand what are the stakeholders that can do this management and what are the agreements between the car owners and the wind farms. but technically it is possible. Afterwards, we have, as Samuel mentioned in previous question, we have these car manufacturers, we have city planners, but we also have the regulation and policies that can play an important role in this. For example, we have this example in Lisbon that the municipality put the tickets free for the young people and limit the prices. And I think more and more persons are using this public transportation. What is important is that this public transportation should be also electric, and this is the key point of this discussion.
Thank you, Hugo. In fact, we are receiving a lot of interesting questions, and we don't have time to put all of them. But I have here another one for you, Hugo, from Gonçalo Mendes. Regarding the parking lots, did you study the role of the bidirectional charging in energy management of the building facility?
Yes, in these two studies, as I mentioned in first one, we don't have any information about state of charge of the batteries and concerning the cars, and we only considering charging. In second study, we have this information, and we consider the possibility to charge and discharge the vehicles, vehicle to vehicle, and so on. Mainly because we have limits, and we imposed hard limits in the power consumption from the parking lot, global parking lot, and to supply all the needs, we need to discharge some vehicles to charge in other vehicles.
Okay, thank you, Hugo. Looking to the list of questions, and now to Fernando from Maguilas. Are there any days in the year that electricity is 100% renewable in Azores Islands? Because in Portugal, in the mainland, there are days in which that happens.
Nowadays, yes, there is. Nowadays, it depends on resources and technology that is there in the island. There are 2 islands that can achieve 100% during some hours. One island is Graciosa Island. It has an innovative project. Since 2020, it can be 100% renewable, and it has already achieved it during about 6 to 7 days. Another island is Flores, and it has many hydro potential, and we can during night turn off all the diesel engines and use only renewable, mostly hydro and some wind, some aeolic production.
Okay, thanks. Another question to you, Fernando, from Gonçalo Mendes. Was the vehicle to grid support from only 10 vehicles visible? What incentives, if any, were set in place, and how feasible do you believe customer remuneration for these services is?
We have been studying that and seeing the ancillary services that they could do, that load shifting and frequency regulation, and trying to see what to know what benefits that it could give to the grid, the system operating from production, transmission, distribution, and we have had some numbers. The vehicle to grid that project was done here in our installation, in system operator installation with system operator vehicles, so there was no money paid to us from us, but we have, with help of Ines Tech, tried to see what benefit it could be have to the grid, and how it could be paid to the customer, to a normal customer. But the values were not very high. It wouldn't be. It wouldn't make the person to select that kind of technology, vehicle to grid technology nowadays. but still we want to do another project and to see if there is other benefits or more benefits that it could get to us, and if it could be paid or reduced in the tariff for the customers. And that's the goal, is that the customer has some benefits from the service that it gives to the grid.
Okay, thank you, Fernando, and thank you all for this great session. In fact, we received many participants, and we are glad for it. Many questions we didn't have. We don't have time to answer all of these questions during this live session. We are going to do it offline. Let me thank you for the attendees for participating in this session. Again, thank you to our speakers, and have a nice evening.
Thank you.
Thank you very much.
Thank you very much.
Everyone, this session will be available on our website. Thank you for your active participation. And just to let you know, we will be having another webinar just like this in a month as usual. So feel free to join us in another R&D session by EDP New. Thank you, João.
See you soon. Thank you all. Bye.